This work is done in collaboration with Alexandre Sauvé, la concierge Lefebvre, Simon Germain, and from Université Montréal, and Gilles Janot and Christophe Domain, EDF for the second part of the talk. Of course, I'm building this on algorithms and methods that I've been developing over the years with a number of people who were involved in it. So Laurent Karim Bellam yesterday, and various support. So I'll be focusing in the second part on high entropy alloys and concentrated solution because I'm cheating, I do modeling. So what I pretend are high entropy alloy, I really do a three-element model, three-element alloys. So it's kind of a fake high entropy alloy. But why am I interested in this? The question is, so we heard about this, I won't go back, but there's some very interesting properties of these high entropy alloys. They're probably misnamed, but you'll see that we found some entropy aspect, interesting entropy aspect in these alloys, which don't match what people typically talk about. One of the interests, so this is funded in part, this project by EDF, so in France, because they're trying to develop new alloys for the next generation of nuclear reactors. I said they barely managed to build the current generation, so that's another story. But so one aspect is that these alloys resist irradiation and show, for example, very low diffusivity of vacancy. So I'm saying here there's a lot of debate about this. Some people disagree totally, other experiment, but let's believe that there's low diffusivity because that justifies why I'm doing. So let's move back. How do we address this? So we're using approaches that are built on the energy landscape. So if you want to look at low diffusivity of the effects, you have to be able to model stuff over a very long time. And long time is not nanoseconds. From people who are doing DFT, they believe that nanosecond is next to the end of the world. No, I'm talking about seconds or years, okay, at the atomic level. So the way to do it is not to just simulate all the oscillations, but really focus on the energy landscape and be able to say, I'm sitting somewhere, I can find the transition state and move to the next state without having to wait for the And so what we do, we can compute the probability of moving to a saddle point, including which is dependent on the Boltzmann weight, of course, delta E over KBT, which is the difference in energy between the two states. And then there's a prefactor which tells you how often you will try to get there and how often you will manage, given really a difference in entropy between these two states, which we can compute, for example, with called harmonic approximation. So I can do just approximation of this is harmonic, and minus the negative eigenmode, and I can compute the prefactor. Turns out it works very well. So there's also a lot of debate on is it a good approximation or not, but it turns out it's pretty good. And I'll show you better. And so to find the saddle point, you need to have methods that are unbiased and that are open-ended, which means you sit in a local minimum and you find a saddle point, okay, locally. And the saddle point is described by a direction of negative curvature in one direction and 3n minus 1 positive curvature at the saddle point. So this is based, we use Art Nouveau, which is a method I've developed a long time ago, almost 30 years ago. It tells you something. I'm slow and I don't have many ideas. And we've been making a lot of progress in the last few years with groups and tubes and peers. And all this is linked into a method which is called kinetic art, kinetic activation relaxation technique, which uses Art Nouveau to find on-the-fly events. So as we move along and we sample new configurations, we need to be able to build a catalog of events. We qualify this catalog with a topological analysis tool, which allows us, even in disordered materials, fully disordered amorphous glasses, to be able to recognize events, to classify them and reuse them over time. And we use what's called kinetic Monte Carlo, which is an approach that tells you, given that I know the rate, with the proper Poisson law, I can select one event and move forward. So I'm really giving you the very brief course on that. We've been using this in a number of systems. For example, we looked at carbon diffusion in iron a few years ago, and that allows us, for example, to do simulation here where we can follow the diffusion, say, over a microsecond. We've done, depending on the bears, much longer, and we can follow what are at grain boundaries, for example, what are the diffusion over a long time, and understand what determines this behavior. For example, we can model and find barriers at 1.7 eV at 300K or 500K, so we get the right kinetics. And this is not very disordered when you look at the grain boundary. So I'm just get used to the method. So what we've also done, for example, we look at the internal dissipation, so two-level states, two-level mechanism in amorphous silicon for the LIGO experiment to understand some basic noise in these experiments. So this is fully disordered materials where we can follow. So if you have more questions, we can come back, but that's the method we're using. So let's now move to the physics. So the issue, it started with trying to understand the law of compensation. The law of compensation builds back on work that was done by Arrhenius already a long time ago. Some experiments here on saying that at the basis, if you look at diffusion, we know that the diffusion is dominated by a prefactor times a Boltzmann weight. Okay? That's known. But what was also discovered more than a century ago is the fact that there's some correlation between the prefactor and this activation barrier. And that's a bit puzzling because the prefactor essentially is a measure of entropy. The barrier, by definition, is a measure of difference in energy. And in principle, those are two properties. One is a static property, the energy. The entropy is an ensemble property. It's not. So these two have been linked, and people have seen this, what is called a compensation law. Why is it? Because if I draw here the energy, and I'll go here. If I draw here the energy and here the entropy of the system, you see that the higher the energy barrier is, the more entropy there are, and therefore it means that this prefactor increases as this term decreases. So it compensates in some way the fact that the barrier is higher by having a higher frequency of atoms. This was known for a long time. And I'm saying you have some data going back to the end of the 19th century. Without a good explanation of this. And it turns out you see this in electronic, which we don't explain, but in the electronic system, you do electron trapping and releasing. You have also this law of compensation. So the first thing we did was, can we recover this law? And initially, when we started looking at this, we thought that the harmonic approximation would fail, that you need to have complex phenomena to explain this behavior. And it turns out that if we look at, this is vacancy in silicon, what we can do is that if we look at the experimental value of this slope, which is this compensation law, which is 3.3 here, we can recover the slope with different empirical potentials, okay, which will give us between 37 to 90% of the slope that is given experimentally. I don't have the data, but if we do it with DFT and aluminum, for example, we recover more than 90% of the slope with pure harmonic approximation. So there's nothing complicated happening to explain this behavior. So once we found this, we said, okay, so how can we explain it? Turns out it's very hard to explain it with a crystalline system because we don't have enough data to be able to extract understanding. So what we did was to say, let's turn at glasses at disordered materials for which we can generate many more events. So this is, for example, 100 configuration of 4,000 atoms of amorphous silicon. And so it is about 1 million events we generate here. Events that go from 1 to 5 eV. We have higher, but we don't include them. We just focus on the kind of lower barrier. Yeah. And what is interesting is that we recover essentially the same slope as in the crystal for the given potential. So we are convinced that we can manage and understand what's happening. To be able to better understand, in fact, we look at force system because every time we had amorphous silicon, when we started looking at this, we found a very nice explanation. Then we checked with another system, it always failed, so it took us some time. So we decided to make it for system. We have so amorphous silicon. This is a glass copper zirconium, nickel phosphide, and Lennard-Jones. It's very interesting. I'll take a step. This is the prefactor as a function of the energy barrier. Okay. In silicon, you see there's a very good correlation between the prefactor and the barrier. On average, if you are here, you see it's almost flat, slightly negative, but it's puzzling because you have here so what we did was, what happens to the shift in vacancy? So what we look here is, I have the V dust at the minimum. I had the V dust at the vibrational density of state at the saddle point. And that's what I will do the ratio of these two. And because I have a million events, I can easily separate this and get statistics for different barriers along my system. So I can get very clean data on this. What you see here is that if there was no shift, you would have something which is flat, so the ratio is 1. What happens at low frequency, you see that there are modes that are being shifted when you go from the saddle minimum to the saddle point. They are being shifted to lower frequencies. Then they are shifted by depleting this region. And from 4 on, they are shifted to higher frequency. You see the same thing in amorphous silicon. At low frequency, they are shifted to lower frequencies. And as you move away, they are shifted to higher frequency. And it turned out that this point where you shift to low to high is essentially linked to the moment where you go from delocalized to localized. So there's a direct connection between localization and this shift. And if I go further, what you can still see is that essentially when you shift to local mode, and what I'm showing here is the kind of what happens to the prefactor, okay? Now what I'm doing is I'm multiplying and I'm saying, how is the prefactor changing as I'm adding mode and mode and mode in my ratio of for computing the prefactor, the ratio of vibrational frequencies. You see that as I shift to lower frequency, you might not remember, but when we look at the prefactor, is the ratio of the vibrational modes, the frequencies at the saddle over the frequencies at the minimum. Sorry, it's minimum over saddle. As we shift to lower frequency, we're increasing the frequency of the prefactor. And as we move forward, because we're now piling up more and more modes at high frequency, the prefactor shift, and in this case, becomes the while in amorphous silicon, it moves to positive. So all this, and I know it's a bit quick, but it works also in the other system. But essentially, what happens is that in these systems, the connection between the energy and the prefactor is the following. If you have, and it comes to the structure, okay? Why is Lennard-Jones? So Lennard-Jones and amorphous silicon behave in different ways. So let's go first at amorphous silicon. So ultra silicon is a very open structure. When I'm activating to a saddle point, what I'm doing is that I'm stretching bonds. So I'm weakening locally the frequencies. So I'm shifting most to lower frequencies. So as the barrier is higher, I'm weakening more and more the local network, and therefore I'm increasing the frequency and then increasing the entropy. If I'm in something very dense like Lennard-Jones, it's very, very stiff material, Lennard-Jones. So if I want to activate, I have to push and pressure and really increase the energy locally. And this increase in energy will mean that my modes are being strengthened, the vibrational mode, and this will contribute to this decrease in entropy. And so we can link energy and entropy here due to the structure, the local structure of these materials. And this allows us to really explain a number of properties, impact of impurity and all this, or in fact, there's no impact on impurities when you look at these things in these systems, by really linking through the structure these materials. So that was interesting because that solves a problem which is 100 years old, at least on systems which are structural. So let's go back to this and what's the link? Well, we had seen in in metals that you have often a very high distribution of in glasses and glassy metals, high distribution of prefactor for the same barrier. So we were looking at this kind of high entropy alloy, so really this kind of iron, nickel, chromium concentrated solid solution. And so we looked a bit at the effect of the prefactor. And it turns out that in these systems, which are disordered but on a crystalline basis, so it's a crystalline lattice, FCC lattice, you have three different elements that have almost the same size, okay? There's very little size distribution. And yet, if I look at the prefactor for a vacancy jump, so this is for a vacancy that jump in this system, we find that the energy is very similar between the various jumps between the environment, because you have a disordered environment. And yet you have here more than 4 orders of magnitude in the change in prefactor. So the question in this, and we try to identify what's the correlation, and essentially we find very little correlation with the local environment. And we find essentially the main correlation is with the local pressure. So what we find is that the higher the pressure, the local pressure is, which we can compute the material, the lower the prefactor. But you see, it's very noisy. So we have this trend, but it's not a very good thing. So we still don't have a good explanation for it. So what we did then was to look at kinetics and to see it's nice that we have different prefactor as a function of the inner for the same barrier, for the same mechanism. But the question experimentally is that we know that there's a change in kinetics. There's a slowdown in kinetics for these defects. At least that's what some experimental report. So what's the effect of having a prefactor that changes on the kinetic of the system? And what will be the effect of the diffusion of the vacancy, which almost has the same barrier, given that you have this large prefactor there? So what we did was to generate, again, millions of events. So we have a fairly smooth distribution. What you have here is a distribution of barriers for the first, essentially the vacancy jump. This is all the barriers that are being generated in the catalog, and this is the selected barrier. So not surprisingly, even if I generate high energy barrier, I will tend to visit lower energy because of the prefactor, because of the Boltzmann wave. Same thing, this is all the prefactors that I'm computing. And of course, I will tend to visit the higher frequency prefactor that move the furthest. So there should be some correlation between all that. And this is a bit what we look at and what we find. For example, what we find is that even though around the vacancy, as it moves around, the vacancy doesn't really visit environment that are fully representative of the average composition of my system. And it's a random solution between it. So, and the species moving is also both different from the environment it is visiting and very different from the type of mechanism there is. So there are strong biases in the kinetic of these systems that need to be understood. And if you look at all generated events, what I'm showing here is the barrier, and I can go back and look at the various species. And essentially, clearly that explains why, for example, chromium is over-selected, even though it's relatively low in proportion. It has low barrier, and it has therefore a lot of space to be visited and being selected. I already discussed the prefactor. The time is flying, so I'll just move here. Before I showed you this graph here for the glasses, so where I show the prefactor versus the barrier. And what you see here is that the compensation law typically has a slope which is positive. Here, if I'm in Aaron, when I take all the mechanism, I have a slope that is slightly negative, almost zero for the equivalent from Young. If I look only as the selected event, in the selected event, I tend to take the lowest energy barrier with the highest rate. So I'm biased over what happens here. And what is interesting here is that I recover, in all cases, the compensation law that is seen experimentally in terms of slope. And yet, so I find the right kinetics. I find that not all the events are selected the same way. And then what I can look at here, and I can finish with this, is what's the impact of using the right prefactor, and what's the impact of the prefactor over there? So we did a simulation where we only take a prefactor that is constant, and we only focus on the barrier for the diffusion. We did a number of simulations. And this is the slope we get for the diffusion. So we get a faster diffusion than when we start putting in a prefactor. Even though the average prefactor in both simulations is the same, 10 to the 13 hertz, because this correlation between prefactor and barrier, it means that we're diffusing slower in this system. And the fact that we include the entropy, interestingly, means also that we relax less the system. So the entropy tends to keep the system from separating, phase separating. This is an unstable composition. So it keeps it from separating. It slows down the kinetics. And the interesting thing of all this is that it's the entropy that drives this. But it's not the compositional entropy, which is what people refer to when they call about this high entropy alloys, the fact that you have a complex composition. It's really the fact that the prefactor plays a huge role here while the energy of the diffusion is very limited. The point is we did all this with empirical potential. So will it remain if we do better potential? And of course, that's where machine learning potential are useful because we cannot do this type of simulation with PFT. And what's the impact in other systems? In other systems that are a bit complex, where for a long time we kind of neglected this possibility because in a lot of systems, essentially the prefactor is constant at the given barrier. It's really as you change the barrier height that you change. So those are a lot of questions that remain. This is fairly fresh work, so we haven't had time to do everything. Kinetic art is applied to a lot of other systems that I'm not mentioning. We've done a lot of effort, and we're implementing, in fact, machine learning approaches to recover mechanism and things like this. But we're not at the level where we can discuss it now. So I will stop here and thank you for your question. Yes.
I think you show the figure like where we have low vibrational frequency and all is related to a collective atomic vibration. More atoms are collective vibrations.
Sorry?
It's like for low vibrational frequency, the more atoms are involved.
Yeah.
Yeah. So it doesn't mean that temperature is high enough, all atoms vibrating. We can always use the binder for all diffusion atoms.
No. This is really if you think of phonons, for example, in a crystal, irrespective of the temperature, phonon is a delocalized object, is size of the bug, okay? If you are in a disordered system, most of the vibrational modes are delocalized. It's only around, no, typically it's the regions where you have a lot of constraints or a lot of tension, you can localize. This is Anderson localization, or there's a few localizations, but essentially this localization is due to the disorder. It's not, and the difference in disorder. So overall, most of the modes are delocalized, even at high temperature. And when you, until, even in a liquid, you have vibrational modes that are formally delocalized.
Time for one more question. Yep.
Yeah, very interesting. So we've seen a lot of work on predicting energy from machine learning, and entropy is also a big thing. Vibrational mode calculations can be very expensive.
Yeah.
So do you think there's scope? And you've already shown there's a correlation with that. Your scope to also use machine learning.
Yeah, we have a paper with Cosmin Marinitsa, who is the main author at SACLI. We've done some work on this based on these data sets.
So what are the main inputs? Is it just that geometry is the biggest factor, or you?
Yeah, geometry is it's what we did was built on geometry only.
Very good. Let's stop there, but thank Norman again.
Thank you.